Hello students, in this particular video lecture in part number 9 of unit number 4, I am going to discuss with you people the procedure to determine the final end moments in distribution method, in moment distribution method. Basically, my dear students, if a beam is having only one span or maximum two spans, or if a frame is having only one story, then directly the fixed end moments can be calculated using the formulas which we had discussed in our previous video lecture. But if spans are large, then obviously at intermediate location there must be a rigid joint, and as we know that distribution factor at rigid joint must be equal to 1. It means all the moments must be balanced. Algebraic sum of all the moments at that particular rigid joint must be equal to 0. However, if the moment is not 0, if the algebraic sum of all the moments is not 0, then we have to apply a balancing moment to that particular rigid joint. That balancing moment will get distributed in all the members meeting at that rigid joint in the proportion of their distribution factor. In the proportion of their distribution factor. So, my dear students, if I am talking about the stepwise procedure to calculate the final end moments using the moment distribution method, our first step is we have to calculate the fixed end moments by assuming both the ends, outer ends of the structure locked or restrained. The sign conventions will be clockwise positive, anti-clockwise negative. The second step will be at a joint where more than one members or more than two members meets, at that particular joint we have to calculate the distribution factor. Third step, we have to calculate the balancing moment. If the algebraic sum of all the moments meeting or for the members meeting at a rigid joint is not equal to 0, then we have to apply some balancing moment. Fourth step, we have to distribute that particular balancing moment in the proportion of their distribution factor for the members which are meeting at a rigid joint. Fifth step, carryover moment will be half of the applied moment if the far end is fixed. However, if the far end is hinged, then no carryover moment will be there. So, my dear students, for that case, if the far end is hinged, for that case, end correction is applied. We have to apply an end correction. You can say the moment must be equal to 0 for roller and hinged spot. If there is some moment at the hinged support, then we have to make that moment equals to 0 by apply some end correction before starting of the cycle of the moment distribution method. We have to repeat all these steps for more and more accuracy of the calculations. And at the end of the table, we have to add all the moments, which gives me the final end moments. On the basis of these end moments, we have to draw the end moment diagram. Then we have to draw the simply supported moment diagram. Then we have to superimpose both these diagrams to get the final moment diagram. This is the stepwise procedure. Okay, my dear students. So the first step is we have to calculate the fixed end moments. Find fixed end moments. Find the fixed end moments by for each member at both the ends. At both the ends by assuming both ends as locked or fixed. By assuming both ends by assuming both ends as fixed or locked. By assuming both ends as fixed or locked. The first step is we have to find the end moments for the each member at both the ends by assuming both ends as fixed or locked. Please be careful here. The sign conventions are positive for the clockwise moments and negative for the anti-clockwise moments. Positive for clockwise moments and negative for anti-clockwise moments. That's okay? Okay, now step number 2. We have to calculate the distribution factor for each member at those joints where more than one member meets. Calculate the distribution factor for each member at those joints where more than one member meets. At those joints where more than one member meets. Or you can say that is the joint is rigid and joint is rigid. Please be careful. Distribution factor summation at the rigid joint must be equal to 1. That is, algebraic sum of distribution factors at rigid joint must be equal to 1. Algebraic sum of all the distribution factors at rigid joints must be equal to 1. Now, third step. Basically, we have to calculate the algebraic sum of all fixed end moments at the rigid joints. Step number 3 is very important. Please be careful. On the basis of this step, the complete numerical is basically based. So, find algebraic sum of fixed end moments. These fixed end moments. Find algebraic sum of fixed end moments at rigid joints, and if the resultant is unbalanced, means if summation of all the moments is not equal to 0, and if resultant is unbalanced, that is algebraic sum of all fixed end moments is not equal to 0, and if resultant is unbalanced, then we have to apply a balancing moment, and that balanced moment will get distributed in all the members meeting at that rigid joint in the proportion of their distribution factor. Then apply a balancing moment Please be careful. Magnitude of this balancing moment will be equal to this unbalanced moment. Let us suppose that unbalanced moment is -5, for example. Then we have to apply +5 because we have to compensate that particular unbalanced moment. Then apply a balancing moment, and this balanced moment and this balanced moment will get distributed in all the members in the proportion of their distribution factor, and this balanced moment will gets distributed in all members meeting at that joint, in all members meeting at rigid joint in the proportion of their distribution factor, in the proportion of their distribution factor, in the proportion of their distribution factor. Fourth step. If I am concluding about these three steps, initially we have to calculate the fixed end moment, then we have to calculate the distribution factor, then we have to calculate the unbalanced moment, and we have to apply a balancing moment. This balanced moment will get distributed in all the member meeting at that rigid joint in the proportion of their distribution factors. Okay, that's okay. Now, if far end is fixed, carry over moment will be half of the balancing moment. Half of the balancing moment if far end is fixed. If, as we know that we have calculated the carryover factor for when the far end is fixed, that was 1/2. When the far end is hinged, that was, and you can say that depends upon A by B ratio at extra parameters, and if a far end is you can say free, that becomes the value 0. Carryover factor is equal to 0. If far end is fixed, then carry over moment, or you can say the distributed moment, with whatever the distribution will be there for the balancing moment, then distributed moment will carry to far ends, and then these distributed moments which are carried to the far ends are called as the carryover moments. Carryover moment is half of the distributed moment or the balancing moment. Half of balancing or distributed moment. Basically, my dear students, I have dictated in detail these steps because now it's okay for you people. There is no problem now. But when you will revise the subject, then you will find a lot of difficulties if I will not dictate these steps. That's why I have dictated all the steps in detail, because during the revision these steps will become very, very helpful for you people. These steps will play a very important role during the revision. Okay, so if far end is fixed, distributed moment will carry to the far ends, and carryover moment is equal to the half of the balancing or distributed moment. It means, what I want to say, carryover factor is equal to 1/2. What I want to say, carryover factor is equal to 1/2. Okay. Now, for multi-span cases, 3 to 5 steps from step number, or 3 to 5 repetitions from step number 1 to 4 has been done to get the accurate values. Please note it down very fast. After that, we will discuss the next step. Okay. So for multi-span cases, 3 to 5 steps of repetition for multi-span cases, I will, don't worry, I'm writing, just wait. Okay. So my dear students, our fifth step is for multi-span cases, 3 to 5 steps of distribution are done or repetitions are done. For multi-span cases, 3 to 5 steps of distributions are required. 3 to 5 steps of distribution are required. That depends upon the accuracy. Distribution are required depending upon the accuracy. Depending upon accuracy desired. Depending upon accuracy desired. If more accuracy is desired, then only 5 steps are there repeated. Otherwise, 3 steps are sufficient. The final end moments are calculated by taking the algebraic sum at the end of the table. The final end moments, please be careful, these are final end moments, not the final bending moment. Final bending moment will be the sum of algebraic sum of final end moment plus simply supported moments. Final end moment at each end are found by taking algebraic sum of all the steps. Found by taking algebraic sum of all the steps. Algebraic sum of all steps at that joint. Taking the algebraic sum of all the steps at that joint. For multi-span cases, 3 to 5 steps are required depending upon the accuracy desired, and the final end moments will be equal to the algebraic sum of all the steps at a particular joint, at every joint of a structure. Now, if final end moments are known, then the end moment diagram can be plotted and superimpose it over the simply supported moment diagram to draw the final bending moment diagram. So step number 6 is draw the end moment diagram. Here negative using the final end moments, using the final end moments. Here negative values are plotted above the beam and outside the frame. Here negative values are plotted above the beam, outside the frame, and similarly positive values are plotted below the beam and inside the frame. Below the beam, inside the frame. Okay. Now we had drawn the end moment diagram. Seventh step is also draw the simply supported moment diagram. Draw simply supported moment diagram. Simply supported moment diagram using equations of equilibrium. Using equations of equilibrium. Using equations of equilibrium. Now eighth step is superimpose the end moment diagram over the simply supported moment diagram to get the final bending moment diagram. Superimpose the end moment diagram. Superimpose end moment diagram over simply supported moment diagram. Over simply supported moment diagram to get the final bending moment diagram. To get the final bending moment diagram. A moment diagram in which common area is being neglected and the individual area is being considered. Common area is being neglected and the individual area is being considered. Now this was about the, if I am concluding the steps, initially we have to calculate the fixed end moments, then distribution factors, then balancing moment, then that balancing moment will be carry over and to the different members meeting at a joint. Then for multi-span cases we have to repeat all the steps 3 to 5 times. We have to draw the end moment diagram using the final end moments. We also have to draw the simply supported moment diagram using the equation of equilibrium, so summation fx0, summation fy0 and summation mz0. Superimpose the end moment diagram with the simply supported moment diagram to get the final bending moment diagram. Now basically two important points are there. One is, if the far end is fixed, then there is no problem because the balancing moment or distributive moment will be carried over. Actually half of the balancing moment will be carried to the you can say when the far end is fixed to that member. But if the far end is hinged, then that moment or end moment will not be carried over. Distributed moment will not be carried over to that particular member. Since as we know that at the hinged end or at the roller end, the moment is equal to 0. So to get the moment value equal to 0, we have to apply some correction. That correction is called as the end correction. However, if the intermediate support is roller or hinged, then there is no requirement of application of the end correction, because by the continuity or by virtue of the continuity, the intermediate support will get converted into a rigid joint. That's why at the intermediate support, whether it is a roller or whether it is a, you can say, a hinged support, then there is no requirement of the end correction, because by virtue of the continuity, that particular joint becomes the rigid joint, that becomes the fixed support. Okay, so please note it down very fast. Please note it down very fast. Okay. Okay, so very important notes are there. Note number 1. Generally, the fixed end moment are considered by assuming both ends fixed. But if one end is hinged, generally fixed and moments are considered by assuming both ends fixed. This is the first assumption. In first step, assumption was there by assuming both ends locked or fixed. By assuming both ends fixed or locked. But if one of the end is hinged, if one of the end is hinged, but if one of the end is hinged or roller, then then end moment at that joint will be 0. Then end moment at that joint will be 0. End moment at that joint will be 0. Therefore, some end correction is required. End correction is required, and hence you can say, therefore, I will apply the end correction, don't worry. I will apply the end correction, don't worry. Therefore, some end correction is required. But please be careful. If intermediate support, if roller or hinged is intermediate, then end correction is not required. If roller or hinged is intermediate, then end correction is not required. Then end correction is not required. Then end correction is not required. At roller, bending moment should be 0. So we have to add some negative moment in the place of some end correction. In the place of some end correction at roller or hinged support, bending moment should be 0. Bending moment should be 0. Therefore, we add some negative moment to get the value of the bending moment equal to 0 as in the place of end correction. So we add negative moment So we add, or we have to add some negative moment, but half of this negative moment will be required or supplied to the far end if the far end is fixed. But half of this moment will be supplied to far end, but half of this moment will be supplied to far end and will be added to the previous value. For example, I had applied a negative moment here, then I have to transfer this moment half to the next value, and we have to add this to the previous value to get the final values, and after that we have to start the cycle of the distribution table. We have to start the cycle of the distribution table to the far end and will be added to the previous. Values. These are the important notes about the moment distribution method. Generally, the fixed end moments are considered only, you can say, at the fixed ends. If the one of the end is hinged, then end correction is required. At bending moment at roller or hinged support, the bending moment should be equal to 0, and if it's not 0, we have to add some negative moment. This negative moment also gets distributed to the, or you can say half of this moment is distributed to the end, it will be added to the previous value to start the cycles. Now let's apply all the steps to a numerical, only then your concepts will be clear. Okay, please note it down very fast. After that we will start the questions of moment distribution method. We will start the questions of moment distribution method. Okay, so the first question is, please be careful. The questions of moment distribution, slope deflection and matrix method are more important as compared to the questions of strain energy method. Those questions are more important. Okay, so my dear students, please write down the question. After that we will discuss its solution. Question number 1. For the beam as shown in the figure, draw the bending moment diagram using moment distribution method. For the beam as shown in figure, draw bending moment diagram BMD using a moment distribution method. and the beam is given in front of you. This is our fixed end, and also this is another fixed end. Also this is another fixed end. This is the fixed end. This is the fixed end. This is 4 meter at center location. 24 kilonewton load is there, 4 meter, and here a UDL is there, UDL of 12 kilonewton per meter, 12 kilonewton per meter. This is A, B, C. A, B and C. Okay. EI is constant. EI is constant and B is given as a rigid joint, since the more members are meeting as a rigid joint. Okay, my dear students, we have to basically analyze this beam. We have to draw the bending moment diagram for this beam using the moment distribution method. Okay, initially we have to calculate the fixed end moments, then we have to calculate the distribution factor, then we have to calculate the distribution factor. So let's start the solution. Initially we have to calculate, here two spans are there, AB and BC. Here two spans are there, AB and BC. Okay, so my dear students, our first step is fixed end moment. M fixed AB, M fixed BA at A joint, at B joint, M fixed BC and M fixed CB at B joint and at C joint. Okay, so central point load is there, value is, here the amount will be anti-clockwise, clockwise, anti-clockwise, clockwise. Yes or no? These values will be there or not? This is M fixed CB, my mistake. Yes, over. This is CB. This is M fixed BC, M fixed BA and M fixed AB. M fixed AB. Okay. In the AB span, value is minus PL by 8. Minus of P, total span is 8, whole divided by 8. Because anti-clockwise is taken as negative and clockwise is taken as positive. Value is minus 24 kilonewton. Now, kilometer meter. MBA also PL by 8. So plus 24 kilometer meter. UDL over entire length, value is minus WL square by 12 minus WL square, that is 4 meter. This span is also 4 meter. Please be careful. 4 square divided by 12. Value is minus 16 kilometer meter. And here the value is plus 16 kilometer meter. That's okay. Step number 1. We have calculated the moments, fixed end moment at all the spans. At all the spans, we have calculated the values of fixed end moments. Now step number 2. Basically only the B joint is rigid. That's why we have to calculate the, you can say, distribution factor only for the B joint. Only for B joint. So second step is distribution factor. Distribution factor, only the joint B is there at which distribution factor needs to be calculated. At joint B, members which are meeting are BA and BC. BA and BC, two members are meeting at this particular joint. Now, what is basically distribution factor? What is the formula? Formula is K divided by summation of K. So initially we have to calculate the value of K, that is the stiffness. For B end, far end is fixed. For B end, far end is fixed. Value is 4 EI by L. So 4 EI divided by L. L is simply 8 meter. L is 8 meter. Value is EI divided by 2. Value is EI divided by 2. And for BC, span is 4 meter. 4 EI divided by 4, value is EI. So we have to add this value to find out the summation K. Summation of K, half of EI and 1 EI, that is equal to, you can say 3 by 2 EI. That is equal to 3 by 2 EI. Now we have to calculate the distribution factor. The formula is simple, K divided by summation of K. K divided by summation of K. K is EI by 2 divided by 3 by 2 EI. Value is 1 by 3. EI divided by 3 by 2 EI. Value is 2 by 3. Algebraic sum of these two must be equal to 1.0, and that's okay. That's okay or not? So my dear students, this is the table of the distribution factor. This is table of distribution factor. Okay, table of the distribution factor. Okay, that's okay. Now third, actually third and fourth step we have to apply in the form of a distribution table. In the form of a distribution table. Okay, so till the time, if I conclude, just I have calculated the fixed end moments. I have calculated the fixed end moments, and fixed end moments are these. Second, I have calculated the distribution factor, and it's 1.0. Now it's time to prepare the distribution table. Let's prepare the distribution table. Before that, please write it down very fast. Okay, so let's prepare the table. Okay, now let's prepare the table. This is our fixed end, and this joint is rigid end, rigid joint. This is A, this is C. Kindly prepare the table on a fresh page. Please be careful. You have to prepare the table on a fresh page. Okay, so after all the values, after calculations, prepare the table. This is R and B. Okay, for this member the distribution factor is 1 by 3, and for this member distribution factor is 2 by 3. Yes or no? We have calculated. Here the end moment was minus 24. Here the end moments were at the joint B. What are the end moments? At joint B, end moment was plus 24 and here minus 16. Here plus 16. Yes or no? Yes. These values were there. So my dear students, plus 24 minus 8, sorry, minus 16. It means the unbalanced moment is basically plus 8. Unbalanced moment is here. Unbalanced moment at B is equal to plus 24 minus 16, that is plus 8 kilonewton meter. So we have to apply the balancing moment. We have to apply the balancing or distributed moment, balancing moment required at B is equal to minus 8 kilonewton meter. So that minus 8 will get distributed in the proportion of their distribution factor. So this is minus 8 into 1 by 3 and this is minus 8 into 2 by 3. Yes or no? Yes. Okay. So far end is fixed. Far end is fixed. This distributed moment will get distributed or will carry over half. Half will carry over to the far end. Half will carry over to the far end. So this value is equal to minus 8 by 1 by 3, that is 2.67. So this value will be distributed and here the value is 1.33. Similarly, here the value is minus 8 into 2 by 3, minus 16 by 3. So the value of half is minus 2.67. So there is no complicated thing because only two spans are there. But if the spans are 3 or 5 or more spans, multi-span cases, we have requirement of more steps. But here no steps is required. Here no step is required. We have to balance the moments. Basically at the end of the table we have to balance the moments. These are the carry over moments. These are the carry over moments. Okay. So minus 24 minus 1.33 at end A value is minus 25.33. These are the final end moments. These are the final end moments. These are the final end moments. Okay. Plus 24 minus 2.63, the value is equal to 21.33 and this value is equal to minus 21.33. This value is equal to 13.33. These are the final end moments. Now you can plot these moments. Now you can plot these moments on a beam. This is the beam. This is beam. Negative value. It means arrow is striking downward side. It means this is our beam. This is the beam. Here the B joint is there. Negative value striking downward side. Positive value, it means 21.33. 21.33. Positive value, it means clockwise value. negative value, it means anti-clockwise value, and positive value, it means clockwise value. Now you can plot the end moment diagram, striking down, striking down, striking down, striking down. So all the values are negative, striking at the bottom face. So the bending moment diagram, end moment diagram will be, this is the beam, this is beam. Since arrow is striking downward side, 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 it means all the values are negative. For plotting purposes, this is our end moment diagram. So here negative value is there, sorry, this value is 25.33, this value is 25.33, okay. So 25.33, here the negative value is there, 21.33, here also the negative value is there, 13.33. So the diagram will be likewise this, all the values are negative, all the values are negative. This is our final bending moment diagram, oh sorry, end moment diagram. This is end moment diagram, okay. Now it's time to plot the, you can say it's time to plot the simply supported moment diagram. As we know that simply supported moment diagram, when the loading is at center, then the maximum bending moment is equal to PL by 4 and UDL loading WL square by 8, yes or no? So here in this particular span, the maximum value is PL by 4, M maximum is equal to PL by 4, P is 24, 8 by 4, that is equal to 48 kilonewton meter, and in this particular span, this is A, this is B, this is C. In this particular span, M maximum is WL square by 8, W is 12, W is 12, L is 4 square divided by 8, so that is 24 kilonewton meter. This is parabolic variation and this is linear variation. 48 here. This is our simply supported moment diagram, positive values there. This is 48 value, okay. Similarly, this value 0, this value 0, and the maximum value is 24. This value is also positive. Now this diagram is simply supported moment diagram. This diagram is simply supported moment diagram. You have basically these values we have calculated so many times. A maximum simply supported moment by considering the effect of loading only, by removing the fixed ends, by removing the restraints, by removing the locking ends. These are the simply supported moments only, okay. Now this is end moment diagram, this is simply supported moment diagram. Just only we have to basically superimpose over each other. The remaining area will be the final bending moment diagram, and the common area is being neglected. Just I have done one thing. I have prepared the distribution table and prepare the end moment diagram and also the simply supported moment diagram. One more thing is also there, my dear students, because at the center of this span value is there, at the center of this span value is there. So basically Also we have requirement of the value of the end moments at the centers of end moment diagram. At the center of end moment diagram also I have requirement. Here the value will be 25.33 plus 21.33 divided by 2. So average value is minus 25.33 minus 21.33 whole divided by 2. So average value is, and let me check the value of average, that is equal to 23.33. This value is 23.33 because of, you can say, the linear variation. Because of the linear variation, this value is there. Okay, now also here the linear variation is there. It means also we can calculate the value of the average moment at the center of a span, at the center of a span BC. At the center of a span BC also we can calculate. This is B, C, this is A. Okay, so here at the center value is 21.33 and 13.33 average, minus 21.33 minus 13.33 whole divided by 2. So the average of these two values is there here, at here. Okay, so this value is 21 and 13, that is equal to 6.67. No, not 6.67. I have to calculate. 21.33 and 13.33 whole divided by 2, that is 17.33. That is 17.33. Why these values are required? Because we have to superimpose this end moment diagram to the simply supported moment diagram, and the net resultant, to find the net resultant values, these average values are required. These are the simply supported moments. These are the simply supported moments by considering effect of loading only. By considering effect of loading only. Now it's time to superimpose the simply supported moment diagram to the, you can say, end moment diagram. Then we can also draw, we can easily draw the final bending moment diagram using these two diagrams. Please note it down very fast. Please note it down very fast. Okay. So let's superimpose the values. Let's superimpose the values. Okay, let's discuss. This is the member AB. This is A, this is B, and this is C. Okay, now initially draw the end moment diagram. This is 25.33. Okay, and this is 21.33. and this is 13.33. okay, now the variation was likewise this. Variation was likewise this. okay, the average value here at the center of span AB and BC were, here the value was 23.33 and here the value was 17.33. that's okay. Now these all values are negative in moment diagram. Now at this particular location the value is positive 48, value 0, value 0, value 0, 0, and here the value is 24, value is 24. This variation is linear, this variation is linear, and this variation is also linear. okay, but this variation was parabolic. This variation was parabolic. Now this is our simply supported moment diagram. Now common area is being neglected. Only this negative area will be there, this positive area will be there, this negative area will be there, this positive area will be there, and this negative area will be there. okay, in the final moment diagram only these areas will be left. okay, so this is the final bending moment diagram. Now you can calculate the net resultant values of final bending moment diagram or final bending moment values for this particular area. Only the hatched area is the final bending moment diagram. okay, only the hatched area is the let us suppose that this is A1, this is B1. At A the final, this is our final bending moment diagram. Now what are the values of final bending moments? Final bending moments. At A the final bending moment is minus 25.33 in kilonewton meters. At A1 the final bending moment will be equal to 48 minus 23.33, that is equal to 24.67 kilometer meter. At B joint value is minus 21.33. At B1 point value is 24 minus 17.33, that is equal to 6.67, and at C value is minus 13.33. These are the values of a final bending moment diagram at A, at A1, B, B1 and C. okay, at A this one value is there, A1 this one value is there, B this one value is there, B1 this one value is there, and at C this value is there. okay, these are the values of final bending moments. Please note it down very fast. After that we will discuss some more questions of moment distribution method analysis. Please note it down very fast. okay, so my dear students, in this particular video lecture I had discussed with you people the procedure of moment distribution method, how the, you can say, final bending moment diagram is drawn with the help of the moment distribution method, and also we had discussed about one important problem of moment distribution method. In the next upcoming video lectures, I will discuss the more complicated problems of moment distribution method. Here the theoretical portion of moment distribution method is over. Only the sway analysis of, you can say, frames is remaining in the moment distribution method in theoretical portion. We will discuss in next upcoming video lectures, followed by their numericals. Thank you so much. Goodbye and keep learning. Thank you.